if you're talking about rotational inertia is L, and the analog of mass is I, and the analog of velocity is omega. And these all need to be conserved, or the inertias need to be conserved. So just like linear momentum needs to be conserved in a collision, angular momentum needs to be conserved in whatever. Increasing your distance, decreasing your distance, speeding up, slowing down. So. You made it! Yes. You're just in time to be our guinea pig. Yes. Stand on that spinning disc. Over here. Yeah. Put your back down and stand on the spinning disc.
Okay.
Put your arms out. Hold on to these dumbbells. You know where this is going?
Yeah.
Okay. And bring them in close together. Okay. Out. Here we go. Spinning. Bring them close together. Spin, 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 spin. Then bring them out again. Woo! Look at that. You can try all you want. It'll be here all day.
That's so cool.
Okay. So just like linear momentum has to be conserved unless there's an outside force, angular momentum has to be conserved unless there's an outside torque. So again, and in this class, again, don't worry about the math. We'll put off the math till next year. When you see people who are seniors in this class last year, remember angular inertia, they'll be like, no, and they'll curl up into a little ball. And suck right down, angular inertia. Okay, questions? Then let's go. Oh, this is fine. Foxtrot. Foxtrot's like,
I see torque.
yeah, there's velocity and there's torque in there, and there's inertia. This is inertial angular inertia and launching. Okay, so I mentioned earlier this week, that if you drop a yo-yo, and I showed you it doesn't fall with free fall, because some of the energy is going into rotational kinetic energy. So when a yo-yo is dropped, it has potential energy gravitational. Now if you just drop it without a string, all that potential energy is going to turn into kinetic energy. But if you let it spin, then the gravitational potential energy turns into linear kinetic energy and rotational kinetic energy, which once again, we're not going to do the math for rotational kinetic energy until next year. But just thought you'd enjoy that. Okay, next. We're almost done. Next, we're almost done with rotational motion. If you have 2 cans of soup, one can of soup is frozen, and one can of soup is thawed. It's chicken noodle. It's mostly, there's about 50% broth. If you take those 2 cans of soup and you roll them down the ramp, yeah, the question is, which one gets to the bottom first? The frozen juice or the thawed juice? Yeah.
Are they full?
Yes, they're both full. They're both unopened. You went to the store, you bought 2 cans of Campbell's chicken noodle. You froze one, let the other one thaw. You're going to set them on the same ramp and let them go. They're going to roll down. Which one will get to the bottom first? I'm not going to tell you. This is a challenge slide. Okay, universal gravitation. You guys know who these people are? Who's that? Aristotle. Who's that?
Great job.
Galileo. Who's that?
I don't know. Edison.
Isaac.
Newton. Isaac Newton. Yeah. And who's that?
Isaac.
Grandpa. No, Isaac. Isaac Newton. And you probably don't know who this guy is because this guy only did the math. If you're not, yeah, this guy's named Cavendish. This guy's named Cavendish. So here's what happened. It used to be thought for thousands of years that since heavy objects hurt more when they land on you, they must also fall faster. That was Aristotle. Aristotle didn't know what he was doing because he was a philosopher, not a scientist. Galileo came up and he apocryphal. This story is apocryphal. Basically, it's like a parable. Basically, Galileo dropped two rocks, one big rock, one small rock, from the Leaning Tower of Pisa, and he had two physics students down below. And did he hear ow, ow, or did he hear ow? Ow. He heard one ow. Okay. So we know that objects fall at the same rate regardless of their size. That was fine. And then this guy named Johannes Kepler came along. And Kepler was an astronomer, and what he noticed is the falling of celestial bodies, the moon around the Earth and the moon around the sun around the center of the galaxy. He basically realized that they fell a lot like objects falling on Earth. So he came up with this crazy idea that objects travel in elliptical paths, and he has some math. The math is right up there, Kepler's third law. If you want to learn about Kepler's third law, take physics AP. And then Isaac Newton used Kepler's third law, or Kepler's laws, Kepler's information, and he said, that's interesting. The force of gravity that pulls the moon around the Earth, and the Earth and the moon around the sun, is pretty much the same as an apple falling from a tree. And he said it varies with the square of distance. In other words, when you are closer together, you have more force. Twice as close means 4 times as much force. Does that make sense? And for him, he realized that it didn't matter if it was an apple falling from a tree towards the Earth or the Earth falling towards the sun. It's the same. The relationship holds that the closer you are, the more force you encounter. Now, we don't encounter this in real life because it's very hard to get further away from the Earth or closer to the Earth. Even when you're in orbit, gravity is about 9.75. Okay? But if you dug down really deep, dig, gravity towards the center of the Earth would get higher and higher and higher as you get closer to the center of the Earth. That's the idea. Okay? So that's what Newton did. And he basically came up with this idea of universal gravitation. The force of gravity is equal to the gravitational constant, which he didn't know, multiplied by the masses of both objects over the square of their distance. Now, what does this mean? It means that Ian, having mass, is attracted to Lane, who also has mass. Because they both have mass, Ian is attracted to Lane. But Ian is more attracted to Taylor because she's closer together. In fact, being a third as close, she's 9 times more attractive than Lane. Get the idea? So Ian is attracted to Lane because they both have mass. But Ian is 9 times more attracted to Taylor because Taylor is 3 times closer. You can do this when you ask out your prom date in the spring. Say, hey, I notice you have mass. And I have mass. So we're attracted to each other. And she's going to respond like this. Oh, that's a good point. I'm going to eat some donuts so I have more mass. I'm more attractive. Yes, the more donuts you eat, the more attractive you'll be. Okay, so basically Newton postulated that anything with mass is attracted to anything else with mass. And whether it be the sun attracted to the center of the galaxy, or all the other stars, whether it be the moon and the Earth attracted to the sun, falling towards the sun, or whether it be your mom attracted to the sun, which is much, much bigger. It doesn't matter. Anything with mass has anything else with mass. Now then there's this Cavendish guy. This Cavendish guy you've probably never heard of. He created something that's called the Cavendish balance. He basically took a teeter-totter and turned it 90 degrees, and he put a fat kid on one end, and another fat kid on the other end, and then he put another fat kid standing up, and another fat kid standing up, and what happened? The fat kids attracted to each other. No, they didn't use fat kids. What he used is really, really heavy balls he really used really heavy balls of lead. Looks like this. He put a giant ball of lead on the floor, and another giant ball of lead on the floor. And then he hung between them a metal bar, and he put 2 more smaller balls of lead on either end of the bar. And what did the bar do? It moved. This lead bar is attracted to this lead bar, or this lead ball is attracted to this lead ball is attracted to this lead ball, and what's even better, they moved in such a way that he could calculate their acceleration. Because they moved with the d equals 1/2 at squared. And you knew the distance, you knew how long it took for them to touch, you used the acceleration. Because of that, he was able to solve F, and knowing the forces, knowing the masses, he came up with G, and G is called the Cavendish constant. Unfortunately, people still call it Newton's constant, but it's actually the Cavendish constant of 6.67 times 10 to the negative 11. That's the big G value, which is printed right there. 6.67 times 10 to the negative 11. Three minutes. You know, I'm not going to give you your homework because you're working on your balances, your torque mobiles. 3 minutes, guys. I have one more thing to talk about. Okay. You understand this, that the idea that everything with mass is attracting everything else with mass? Yeah. The more mass you have, the more attractive you are. The further you are away, the less attractive you are. Okay. Now here's the problem. This was great for a couple hundred years, and then someone noticed that light coming from behind Jupiter showed up before it should have been. We were seeing light behind Jupiter when we should not have been able to see light behind Jupiter. It's kind of like this. If someone stood behind your mom with a flashlight and turned it on, you should not be able to see the light from the flashlight because your mom's in the way. But your mom has so much mass, her gravity was bending the light around her, and you saw the light that should have been behind your mom. You see how this works?
Yeah.
This is what was happening. It's called gravitational lensing. And we couldn't explain it for hundreds of years until this guy named Einstein came along. He says, I got this. Even though light doesn't have mass, light does travel through space. And he said, rather than mass attracting other mass, mass bends space. So just like a fat kid in the middle of a trampoline would bend the path of a marble if you shot past him. So if you shot a marble through a tight trampoline, it's going to move in a straight line. But if you have a fat kid in the middle of the trampoline, the marble is going to bend towards the fat kid. And that's what happens in space, so said Einstein. Sources of mass create gravitational fields which bend space. As far as the light's concerned, it's traveling in a straight line. It doesn't realize that Jupiter's in the way, causing it to move. So as far as light's concerned, it's moving in a straight line, but what's really happening is it's bending around Jupiter. Make sense? So that's the modern theory of gravity. So we're still going to use Newton's laws because everything on this planet obeys Newton's laws because we're not light. But we have to realize that historically we had a lot of trouble with Newton's idea of gravity when we realized that light bent around gravitational fields, like Jupiter or your mom. So that's all we need today. So you can work on your torque balances or torque squabbles tonight. If you want to play with the dish or the disc is going to be right here or over there. Just don't hit each other in the face. According to Interstellar, yes.
And less